day, D, all day.
Let's take a moment now to talk about similar triangles. Just as I said, our special triangles exist to make your life easier. The same is true of similar triangles, because if you have two triangles and you know they are similar to each other, you know a lot about those two triangles that you otherwise would not have known. So what does it mean? How do you know if you have two similar triangles? So let's say I have two triangles here. We can call them triangle ABC, triangle DEF. So if I were to tell you that these two triangles are similar to each other, that would mean that every angle in ABC has a corresponding angle in DEF, which is equivalent to it. So if this angle here is 90 degrees, well, this angle here would also have to be 9 degrees. And if this angle here were 50 degrees, this angle here would be 50 degrees, which would then necessarily mean this angle here has got to be 40 degrees, and this angle here also has to be 40 degrees. And so if you have two similar triangles, it does not mean that all of their angles are equivalent to each other. That would make it an equilateral triangle, and two equilateral triangles would be similar to each other, but not all similar triangles are equilateral. Similar just means that the corresponding angles are equivalent. And so once you know that you have similar triangles, that means all your angles correspond to each other. And it also means that all of your side lengths are in the same proportion to each other. So let's say if I knew AB had a length of 3, then DE in the triangle on the right had a length of 6. So now you know what that proportion is. It is a proportion of 1 to 2. So in this case, then if I were to tell you AC is 4, that would necessarily mean DF here has to be 8. And if BC, the length of 5 is here, would be 10, because the proportion, everything here is twice its corresponding side on the left. Now, what you do not want to do with similar triangles, I should say, the one thing you want to make sure that you do is you always want to make sure that you align your corresponding angles properly. Otherwise, you will not be able to compare them. If you align your corresponding angles properly, you are comparing apples to apples. If you misalign them, you would be comparing apples to oranges. So let's say we have the same example here where I have triangle ABC on the left. This was 90 degrees, 50, 40. Let's say I have the same triangle on the right, except instead of having the 50 up here, I have the 40 up here. That would mean the 50 was down here in the bottom right. And so this here, it's still triangle DEF, but the D is still here, the F is up top, the E is down here. So let's see now what would happen if we try to fill in our side lengths. And so if I were to say AB still has a length of 3, and from here, if you knew your proportion was 2, you might now say, okay, that means DF over here has a length of 6. But we know this is not true, right? Because from over here, it should be DE that has a length of 6. And so the reason this is off is because we did not properly align our angles. So you always want to make sure that you orient your triangles. So step 1 is figure out that they are similar. But then once you figure out that you have two triangles that are similar, always want to make sure that your angles are oriented so that the corresponding angles are all facing in the same direction. Then lastly, last thing about similar triangles is the similar triangle rule. I don't know if there is a more proper name for it. Similar triangle rule seems good enough for now. And so I will just write out the rule here, and then we will take a look at an example of it in our first problem. So the similar triangle rule says, if you have a height that is dropped from the 90-degree angle of a right triangle, then that height splits the triangle into 3 similar triangles. Let's take a look at what this means within an actual GMAT problem. So I wrote the rule out again over here. that we can break it down. If you have a height that is dropped from a 90-degree angle of a right triangle, it splits that triangle into 3 similar triangles. And so let's break this down. First, let's take a look at what our question is. For the triangle shown, what is the length of segment OP? And so OP is this guy over here. And then actually, maybe even before we get to our similar triangle rule, let's just see if we can fill in as much as we can in this triangle. So we know we have a right triangle here. MO is length 3. ON is length 4. OP is X, because that is what we are looking for. And so we should know if this is a right triangle, you can use Pythagorean theorem to say MN be equal to 5. If you were to assume that, for example, MO splits this base here, but if it perfectly bisects it and it splits it into 2 equal sides, and so therefore OP was equal to 4, and B was the answer, you would be making an assumption here. We do not necessarily know that it splits the space evenly. We do not know that MP, for example, is equal to MN. So this is really all we can fill in. And then to fill in anything else, you would need to be able to make some sort of inference, such as your similar triangle rule. So our similar triangle rule says, if you have a height that is dropped from the 90-degree angle of a right triangle here, do we have that here? First, we have this line here, MO. Is this line here, is MO a height? And the answer is yes. What makes MO a height? What makes MO a height isn't this 90-degree angle here. It's not that 90-degree angle here. It is the fact that this line MO forms a 90-degree angle with the opposite side. It is perpendicular to the opposite side. So a height is a line that extends from one vertex of a triangle and then is perpendicular to the opposite side. And you can also say, you can also have a height for a triangle, for example, like this. Triangle looks like this. So you can drop a height from this point here. Call it an AB. AB would be a height here. Now, it doesn't form a 90-degree angle with the base over here, but if you were to extend this base, sort of like an imaginary line here, it still forms a 90-degree angle. So this would still be a height because it's coming from one vertex of the triangle and is technically perpendicular to the opposite base. So this here is a height, MO. And MO is originating from the 90-degree angle of a right triangle. So what makes it a height is this 90-degree angle here, but what makes it fit our similar triangle rule is the fact that it is extending from this 90-degree angle here. And therefore, it should split this big right triangle, MNP, into 3 similar triangles. Now, I said before, so we've inferred now that we have similar triangles, but then you need to make sure that all of your similar triangles, the angles are oriented properly so that they align. And so what I always want to do is, in this case, I got to split these 3 triangles out, and I want to orient everything so it matches MON, because that is how I think of a typical right triangle. It's standing up and facing to the right. And then I want to label as much as I can as I go. So I know MO is equal to 3, ON is 4, MN is 5. So now let's look at the triangle on the left here, MOP, and this is where people can get into trouble sometimes. The reason I can get into trouble sometimes is because now if we're talking about how do I line up MOP so that all the corresponding angles align with MON, well, there are 2 ways you can do that. You can take this point here, P, and you can reflect it over like you are turning the page of a book so that P is now over here. And so what would that look like? That would look like O is still here. And then if we were reflecting this over, M would still be here and P would be here. But I could also just sort of flip this triangle 90 degrees so that M is over here, P is over here, and then O is still down here. So which of these orientations is correct? And the way you can determine that, if you're unsure, is you can just fill in any angle here with any value. Every other angle should then fall into place based on this value, and you can see which angles line up. So if I were to say this angle here is equal to 20 degrees, this is 90, we know we were given that, and so these sum to 110, therefore this angle here must be 70 degrees. And because this angle here, angle M is 90 degrees, that this here must be 20 degrees. Again, we know this here is 90 degrees, and so this angle here must be another 70. And so we can see here, if we're trying to line everything up with MON, the 20 should match up with that angle here, which means this is the proper orientation. It should be do not want to be reflecting our triangle over to the right. We want to be flipping it 90 degrees. And so it is this guy that is correct. This guy that is wrong. Redraw this triangle here. So we have flipped this triangle here, but we can still fill in what we know. So what do we, well, OP is what we are looking for. OM is 3. PM, we don't know. Now here, this is actually, with these two triangles, we're trying to solve for X, and we have enough information here to solve for X, because we can set up a proportion with where we just have a single variable X that we can then solve for. Let's still write out our third triangle. Our third triangle, remember, is just the big triangle, the triangle that we sort of started with before we dropped this height. And so what would this look like if we were to orient it right? And the thing to keep in mind about the big triangle, so the big triangle has its 90-degree angle here, and so that's got to be down here, we know. But then you don't even really have to be able to visualize how you would manipulate this triangle, because we're trying to compare everything to MON, remember, right? And the big triangle shares an angle with MON. It shares this angle here, angle N. And so we know that that should stay in place and be over here, which necessarily means P must be up top. And so if you're trying to visualize how we manipulated this triangle in space, we sort of kept this anchored and flip this, drag this one here under while flipping P up. But even if you don't see that, you don't have to see it, because just knowing that M needs to be here and N needs to stay anchored in place is enough to figure out how it should be oriented. Now, if we were to continue with our labeling, so we know MN must be 5. I don't know the value for NP, but I know it's going to be 4 plus X. Then just as before, PM, we don't really know, so we can't label it. If we wanted to, we can say Z or something. Then everything will be labeled. But we didn't need to do that, right? Because we just want to solve for X, and we already had a proportion just with these two triangles here. So now when we are making our proportion, you can do it 2 ways. I can either say 3 over 4 is equal to X over 3. And that is what I'm going to do. Or you can say something like 3 over X is equal to 4 over 3. You just don't want to mix and match those two things. You don't say something like 3 over 4 is equal to 3 over X. That would not work out. So this side here over this side here is equal to this side here over this side here. So 3 over 4 is equal to X over 3. Now we just got to solve for X. And so cross multiply, 3 times 3 is 9, is equal to 4 times X. X should be equal to 9 over 4. And from our answer choices, it looks like we need this as a decimal. So 9 over 4 is 2 1/4, which is 2.25. That is our answer. C. So in our next video, we will look at triangles inscribed in circles.